Hi, I'm Niladri Shekhar Dutt, and welcome to the short CVPR 2024 presentation of our paper, Diffusion 3D Features, Decorating Untextured Shapes with Distilled Semantic Features. Given a source and a target shape, we want to find a mapping between them to find a corresponding point in the target for a query point in the source. In this example of two fishes, we see that a point on the head of the source maps to a corresponding point in the target. The same goes for the fins and the tail of the fish. In dense correspondence, we find a corresponding point for every single point in the source, which for example can be 100,000 points. Here, we color corresponding points with the same color. Doing so requires feature descriptors which are crucial building blocks in most shape analysis tasks. The ability to extract reliable features from input meshes or point clouds paves the way for not only establishing correspondence, but also extracting low-dimensional shape spaces and learning 3D generative models among other applications. Classical geometry processing algorithms, extensively explored over recent decades, concentrate on identifying geometric invariants. However, these fail to understand semantic features that may not be represented directly as geometric features. Recent methods such as 3D-coded, DPC, and SEORNet require extensive training and are limited in their utility to the trained classes. Given the wide range of meshes available in the wild, a zero-shot feature descriptor is highly desirable. Achieving this in the 3D domain requires a huge amount of 3D data which is not available. In contrast, in the image analysis domain, large foundational models trained on massive image datasets have been repurposed to yield general-purpose feature descriptors. Remarkably, such large-scale models have implicitly learned robust semantic features that match and often surpass classical image feature descriptors. For instance, dynamic features and diffusion features extract dense semantic image features from photorealistic images without additional training. In this paper, we investigate the adaptation of this success to the realm of 3D shapes. We aim to decorate 3D points of a given shape in any modality, point clouds or meshes with rich semantic descriptors. A significant challenge is to address the absence of textures on most 3D models. This is a hindrance as most 3D shapes in the wild lack textures, making their immediate rendering textureless. Image-based feature detectors mentioned earlier work better with photorealistic images. Therefore, we propose to convert textureless renderings into textured images which are rich in details, and in this process extract diffusion features. Adding textures helps to easily differentiate between symmetrical parts of an object, such as this cat. Moreover, as diffusion models are typically trained on very large-scale 2D data, it eliminates the need for additional training or optimization. We start by projecting the input shape to the image space to distill per-point semantic 3D features from images. We sample camera views to produce untextured images from different viewpoints. Creating a realistic textured image from these untextured images requires the model to distinguish between nearby pixels in the semantic sense, such that the visual result satisfies the text prompt. For example, a shading model may color a drawn cube completely gray. Yet, when conditioned on the text iron box, it would be driven to add specific characteristics, such as metallic textures that clearly allow it to be identified as iron. Therefore, we drive a diffusion model to color textureless images realistically and take it to the RGB space by conditioning it on geometric constraints using ControlNet to guide the texturing model. Normal maps and depth maps from the camera obtained during rendering is used to describe the input shape. These geometric conditions along with the text prompt is used to condition ControlNet to produce textured renderings. Note that the generated textured images are not view consistent. However, we shall handle this during feature aggregation. During this texturing forward pass, we extract features from an intermediate layer of Stable Diffusion's UNet decoder highlighted in red. These features are normalized to have unit norm, and the features are aggregated at different diffusion time steps using a weighted approach starting from T/4 to the final denoising step of 0. We assign higher weights to the embeddings from less noisy images. Thus, each pixel gets a 1280 dimensional feature from the diffusion UNet. We further fuse the diffusion features with dyno features extracted from the textured renderings. It has been noted that diner features contain strong complementary semantic signals but are weaker in spatial understanding. Hence, combining the two features gives stronger semantic descriptors while retaining spatial information. We employ a feature fusion strategy where we first normalize the features and then simply concatenate the feature vectors. We leverage known camera parameters during the initial projection to unproject features from the image space back to the points on the 3D input shape. We also employ a ball query introduced in PointNet++ to facilitate feature sharing within local neighborhoods of a surface point. This is particularly useful for shape correspondence, where points in a local neighborhood of the source should match with points in a local neighborhood of the target. To aggregate features from multiple views per point, we compute the mean of the normalized feature vectors. Our rendering setup and unprojection with ball query make the per point accumulated features coherent and enable a simple aggregation. Moreover, we render the 3D shape from several views, which further stabilizes the aggregation, resulting in descriptors that mostly capture semantic meaning. We denoise small inconsistencies in the inconsistent textured images during this feature aggregation step, and this is useful to achieve color and geometry agnostic correspondence. To find correspondence between points of two shapes, we compute their point descriptors independently and match them by cosine similarity in the shared feature space. We present correspondence results on a rematched version of the Shrek 19 dataset to show that our method is robust to topology. As we see, Diff3F can successfully distinguish between symmetrical paths and remains fairly robust under pose and shape variations. To prove the semantic nature of our descriptors, we show heat map visualizations. For a query point in the source, we see semantically similar regions being highlighted in the target shape. For example, we see the legs of the teddy correspond to the legs of the table. Here, the nose of the leopard corresponds to the nose of the airplane. These relations cannot be captured directly by geometry. Thanks to this semantic understanding, Diff3F can effectively handle non-isometric correspondence, as seen in this example of a cow and a camel, where the geometry is very different. Here, the neck of the cow matches with the stretched neck of the camel. Owing to the utilization of foundational models, our method is not constrained to specific classes of humans and animals, and can work effectively across varied categories, such as this pair of electric and acoustic guitar. We compare our method against current state-of-the-art methods, namely DPC and SEORnet. In this example of non-isometric correspondence, we see that DPC can get confused by the radical change in structure, where all points of the dog correspond to the belly region of the cow. SEORnet has largely misaligned correspondences, such as the head, the tail, and the legs are not accurate. In comparison, Diff3F semantic descriptors enable accurate dense correspondence for non-isometric pairs. We show correspondence on shapes other than commonly tested classes of humans and four-legged animals. We see results on diverse shapes encompassing isometric and highly non-isometric pairs to prove the versatility of our method as a general-purpose feature descriptor, such as between an octopus and an ant, and a human and a bust. We see that the head of the octopus maps to the head and the tail of the ant, whereas the 3 legs of the octopus map to the 2 antennas and 6 legs of the ant. Diff3F is primarily a feature descriptor, and these semantic features can be directly plugged into existing pipelines such as functional maps. This is useful in cases where we want to compute a continuous surface-to-surface map rather than matching discrete points. Here, we pass our computed descriptors to a vanilla functional map implementation, which returns a continuous surface-to-surface map that can be then used for direct correspondences. We compare the effectiveness of vanilla functional maps with the wave kernel signature descriptors against ours. Again, we see benefits of having semantic descriptors as it allows functional maps to work with non-isometric deformations, even though they typically struggle with such cases when using traditional geometric descriptors. We report correspondence accuracy within 1% error tolerance with our method against competing works. We establish a new state-of-the-art score on the Shrek 19 challenge and the Shrek 20 challenge, which particularly has non-isometric pairs. Combining our descriptors with functional maps leads to lower average error at a slightly reduced accuracy at low tolerance levels. We compare generalization capabilities of Diff3F against other methods by training it on one dataset category and testing it on another. For DPC and SEORNet, we choose surreal for human shapes and small for animal shapes, as these are the largest datasets for the said categories. Both DPC and SEORNet show significant degradation in performance compared to the zero-shot nature of Diff3F. This highlights the need for a general-purpose feature descriptor. We find that adding realistic textures as opposed to only shading results in a significant improvement in terms of accuracy and reduced errors. We also explore a baseline method using Dino features on consistent textures obtained using texture by Richardson et al. Ours is better, particularly at an accuracy of 1% error tolerance, as diffusion features capture more geometric information than Dino. Additionally, varied texture renderings enable a more robust feature aggregation due to the implicit denoising of unnecessary feature subspaces, such as color. Although our complete approach produces the second best score in every category, incorporating all of our parts together, including fusion with Dino, results in the best overall balance of high accuracy and low average error. K-means clustering can be directly applied to Diff3F, meaning that performing clustering directly in our feature space yields path segments. Here, the elephant and the man are segmented using k=6 and the chair and dolphin using 3. Interestingly, we discovered that the k-mean centroids extracted from one shape can be used to segment another due to the semantic understanding of our descriptors. Here, the cat is segmented using k-mean centroids extracted from the man. This leads to corresponding path segmentation. For example, the arms of the human map to the front legs of the cat, and the head of the human maps to the head of the cat, and so on. For more details and results, please visit our project webpage. Thank you.